Olá a todos, boa tarde. Essa semana a gente vai receber o Orlando Alvarez, da Universidade Nacional da Argentina, de San Juan, da Argentina. Eu vou fazer essa apresentação em inglês. Hello everyone, welcome to this week's Geophysics Department Seminar. I'm pleased to introduce our speaker for this afternoon, Orlando Alvarez, whose presentation is entitled Megathrust Slip Behavior for Great Earthquakes Along Different Subduction Settings from GOCE Gravity Field Derivatives. A quick background on Orlando: he has a bachelor's degree in electronic engineering from the National University of San Juan. He later got his PhD degree in geophysics in 2013 at the same university, where he is now a professor teaching both undergraduate and graduate courses. He's also a researcher at the CONICET, which is the Argentinian National Scientific and Technical Research Council. Before we begin, let me remind you that at the end of the presentation, we'll have a question and answer session, so you may write your questions or comments on the YouTube channel, and I'll read them to him. So thank you, Orlando, for accepting our invitation, and now I'll hand over the presentation to you. Thank you.
Okay. Hello to all. Thank you for you, Gabriel. You're a good friend from Brazil. I've been at the USP many years ago, and I was received with very well by all of you. Well, so I'll do my presentation. Well, I am been working with vertical gravity gradients from GOCE, from the satellite that was launched by Europe many years ago, and we have been working in many different topics as mainly tectonic topics. But after some years of working in different things, I've been inclined to work with Megathrust, because we have found very good results, and I think that the best apport that we can do from this data is in this field, because up to now the resolution of these models is very high, and we can't find little tectonic features, to say it in some way. Okay, so well, I'll make a little intro. When Megathrust, I think that all of you know something about Megathrust, but this is a little introduction. When the Megathrust is the contact, okay, between the subducting plate and the upper plate, as occurs at the Chilean margin, at the west side of South America, where collides with the Nazca and Pacific plate. Okay, this is a great area involucrated in this process. So with gradients from GOCE, we can observe many interesting things. Seismic rupture is an event that occurs when the locked zone ruptures. A great surface slides during the earthquake. Okay, so as a result of this rupture, slip occurs in different points, okay, of this interface, and this is propagated along this region, okay, between the coast and the trench mainly. Okay, this is the main region where this deformation occurs after an earthquake occurrence. This deformation is well characterized by a slip model. And slip model is a kinematic model that describes the quantity, distribution, and moment in which occurs this deformation associated with an earthquake. We have many slip models. We have models for the force slip before the occurrence of an earthquake. We have co-seismic slip models that model the rupture during the earthquake occurrence, and after slip models that measure the deformation in this region in the interseismic time, okay? This work is based mainly on the comparison of GOCE gravity fields with co-seismic slip models. And co-seismic slip models are inverted or are processed from different kind of data. After many years of working, we have found that the best models that agree with our data are those models that include mainly GPS data and INSAR data, okay, data that has a great wavelength. Slip models for same event are a lot of different between them. Here is an example of different co-seismic slip models for the Maule earthquake, and you can see that models are different between them. But after a few years of the earthquake occurrence, where measures are more stable and scientific have more data, they produce models more complex and perhaps more exact that can describe this event. For example, for the Maule earthquake, one of the best models is this that I'm signaling here, which is the model of Moreno, and they combine many kind of data, of different data, okay, teleseismic data, Rayleigh observations, tsunami, GPS, INSAR, yeah, okay. When you make a model with more data, this model is more accurate because data, because of the model depends on data always, okay. There are data that have more information of highest frequencies, and there are data that better represent a longer wavelengths. So they always are quite different. What was the result before analyzing different models? Before the observation of different models, most of them agree with a first patch to the north of the epicenter and to other lobes at the center and to the south of the epicenter. This is, in a general view, all models can describe this slip in 3 patches. But there are some models that represent this better than others. So we will compare for different events around the world with preferably with models that came from, in the same of way, from data that come from a GPS and INSAR, okay? Because the wavelength of this data is more similar to the data of gravity field, okay? It has higher wavelength. Well, there are 2 main points that that we will focus on. After many years of studying the margin or the megathrust, many researchers agree that in most of subduction settings, there is an along strike segmentation for historic and different great earthquakes, and this segmentation is highly related to the relief of the plate that is subducting. For example, in the Chilean margin, all of seamounts, ridges, and fracture zones that are carried by the Nazca plate, these features, or known as high oceanic features, produce a kind of seismic segmentation, limiting the lateral propagation of the rupture along the strike, along the trench, okay, or along this region of the forearc between the coastline and the trench. So there are many different hypotheses about seismic segmentation and earthquakes, but we will follow, or we will center with this point as one of the main points. And in many places, some barriers are persistent along repeated seismic cycles. This is not always so, because some barriers sometimes seems to be there and sometimes not. But in a general and a great point of view, we can say that most of these barriers persist over the seismic cycle, and this put on our head the idea that they are tectonic features control this seismic segmentation. The other point that in which is based our investigation is on two pioneer studies from Song and Simons and Wells, that they observed that, for example, for past great earthquakes as Valdivia or other in Sumatra, they found that slip or the main rupture occurred along gravity minima signal, okay? But at the time of these works that were pioneered, gravity data was not so accurate and has not enough resolution. And from these years up to 5 or 6 years ago, there were no many interesting or important papers based on this relationship. This thematic was almost forgotten. But when we began to work with GOCE data, we found many interesting results that we will explain in this presentation. Well, the method is based on the simple law postulated by Newton many years ago, that by means of a satellite which has its mass, it's possible to map the Earth gravity field by measuring the variations in the distance between the mass of the satellite and the mass of the Earth. By measuring these changes, we can recover the gravity field for the entire world. This has a high advantage because most of models and the study of these regions has been difficult because the known as shoreline problem. The shoreline problem is that instruments, or most of instruments, only measure over the ground, okay, not in the water, with the exception of new sea bottom seismometers, but they are too expensive and not so spread in these margins. So after many years, we now have data that overcomes this problem of the shoreline, and we have a continuous data. This is very important because seismic stations, GPS stations, all of data are brought from the Earth, but not in this region where most slip occurs. So this is one of the most important points for using satellite data as GOCE. Interferometry has the same problem because INSAR don't works over the sea, okay? So only you have only data over the field, over the Earth, okay? So from this data and the new models that combine GOCE with other previous missions as GRACE and LAGIOS, these models achieve a better, the combination of data from different satellites, from gravity satellites, improves the quality of the final data, because GOCE it has a better performance over some wavelength and grace over others. So when you combine both data, you can obtain better results. These models has its better performance at a degree of the spherical harmonical representation of 200. This is a resolution of 100 of kilometers. From the gravity gradient, from the Earth gravity model, we can obtain different derivatives as the geoid, the gravity anomaly, or the vertical gravity gradient. We select or use the gravity gradient because the gravity gradient allows to better reproduce the contact between different bodies and has better resolution than the gravity itself. So as these models have a long wavelength, we have to improve in some way the quality of our image or of the map in which we work. So it's better to work with a vertical gravity gradient that allow to better represent the different masses and contacts. When we process the data, we have to correct from the topographic effect. We performed this with spherical prisms. The software for the topographic correction is a software performed by Leonardo Villeda, and that this software allows to calculate with spherical prisms, and this is important because you have to take into account the Earth curvature. So, well, this is the method that we have used. And when we produced our first map, we found that the Chilean margin presented this kind of lobes of low or minima or negative vertical gravity gradients. These lobes were surprised because we didn't know what this was representing. Then we found that this region was characterized by the deformation produced by these great megathrust earthquakes, and found that most of these lobes of minima gravity gradient agree with the seismic segmentation for historic earthquakes and also for new earthquakes as the Maule earthquake. Then we performed a kind of positive topography from the sea bottom relief, okay, and then extrapolated this to the margin. And we found that this segmentation of the vertical gravity gradient was highly related to the subduction of these high oceanic features. You can see that if you extrapolate the contours of the bathymetry, you can see that this segmentation, in most of cases, is related to the subduction of these oceanic features. But this not only occurs along the Chilean margin. Then we worked to the north at southern Peru, where occurred the Arequipa earthquake, and we found that this segmentation was also related to the segmentation of the gravity gradient was also related to the subduction of these high oceanic features. You can see that when you have a positive relief of the Nazca plate, of the subducting plate, you have a high or positive vertical gravity gradient, and when in the valleys of this relief, you can see that the vertical gravity gradient achieves its minimum values. Then we compare it to historic seismic ruptures and also to new earthquakes that have precise seismic slip models, and found that maximum slip occurred mainly over these minima vertical gravity gradients. Excuse me. You can see that the vertical gravity gradient occurs over this maxima in the signal, okay? And the maximum slip plotted in red line in this profile occurs over minima vertical gravity gradient. This is the case for the Maule earthquake. This is the case for the Valdivia earthquake. You can see that over maxima vertical gravity gradient, slip is reduced, and in the minima of the signal of the gravity gradient, maxima of slip occurred. This occurred also for Arequipa, okay? Minima vertical gravity gradient and maximum slip. Occurred for Illapel earthquake, okay? For the earthquake that occurred on Musin in Ecuador. Almost over the entire South American margin. And then we performed our test for the Sumatra Andaman earthquake. And you can see that again, the relief of the oceanic plate present some peaks and some valleys, and the gravity gradient agree in, we are comparing different frequency signals, but where maxima occurs, almost a maximum gravity gradient occurs, okay? And over the minima of the relief, we have minima in the gradient and maxima in slip, okay? This was performed for Sumatra Andaman. For Nia Simerlewe, you can see again maxima slip occurring over minima vertical gravity gradient. And to the south, in the Mentawai region, you can see for the South Pagai earthquake, the similar behavior. That maxima slip stops the earthquake rupture propagation. Now we are working on Shumahin earthquake in Alaska and observed similar results. And for the Tohoku earthquake of Japan, we also observed that maxima slip occurred over the vertical gravity gradient. Well, this includes the balance to this hypothesis that seismic segmentation is highly related to the subduction of hygrosonic features. These features seem to be segmenting the margin in a high grade, and we propose this is not only observed by means of vertical gravity gradient, it is observed by seismic segmentation, it's observed by the degree of interseismic coupling. And for example, there is another work that analyzes the tectonic segmentation of the Chilean continental wedge, and they observed also that for most of these seismic ridges and seamounts and plateaus, seismic segmentation is related to all of these hygrosonic features that are subducting behind the South American plate. The degree of seismic coupling also is a good indicative of this segmentation, because they have observed that over the subduction of these hygrosonic features occur a higher degree of a higher rate of seismic events of low degree, and don't accumulate enough strength between earthquake occurrence in the interseismic. And in the region between the subduction of these hygrosonic features, interseismic coupling increases as time is passing, okay? So this observed that for the Chilean margin, and we proposed that there are different kinds of barriers to seismic segmentation. There are barriers based on the vertical gravity gradient. There are barriers of first degree. This you can see that here, for example, for Juan Fernandez, the signal of the vertical gravity gradient is more positive, and for the Mocha, for example, and for the Chile triple junction. In these regions, you can see that the vertical gravity gradient is more positive than the other segments, okay? So we propose that these are first order barriers that has a greater power to stop earthquakes or to stop lateral rupture propagation, okay, along strike. And there are other barriers of second order that in sometimes act as barriers, as complete barrier, and sometimes they allow that the seismic energy is reduced, as you can see in the models. The slip is reduced greatly over these barriers of second order, and when the energy reaches the other region of first order, the earthquake is stops. Another thing that we will see is that these high order barriers has a high effect on directivity, but this comes in a few minutes. Well, this correlation between high oceanic features or the seismic segmentation with the vertical gravity gradient can also be observed for the margin of Sumatra Andaman in the region of Indonesia. You can see that for the great earthquake, the slip is reduced in some regions, and again, at the other side is enhanced. And this occurs many times as rupture propagate to the north. And these regions where slip is reduced coincide highly with relative vertical gravity gradient maxima, and maximum slip occurred again over vertical gravity gradient minima. The Nia-Simeulue earthquake is a little difference. We have many explications for this. We have this is a paper that was recently published in Frontiers in Earth Sciences. I have to tell you another thing that we have observed, and is that when earthquakes nucleate close to these positive regions of relative positive of vertical gravity gradient, rupture propagates in the other direction, as occurred for Valdivia, as occurred here for Sumatra. You can see that the earthquake nucleates in this region, and all of the rupture propagates to the north. And this region acted as a main or first order barrier. This region where the vertical gravity gradient presents a relative positive signal. Then for the Nia-Simeulue earthquake, nucleated, but not on a region of change of the signal, but nucleated over the minima. In the cases that the earthquake nucleates over a minima, as occurred for the Maule, you can see that rupture propagates in different directions, and you can observe different patches of enhanced slip in different directions, okay? And this is another analysis that we are performing now. You can see that this region really acted as a seismic barrier for the northern propagation for the Nia-Simeulue earthquake and for the southern propagation of the Sumatra Andaman earthquake. This is a zoom of this region, where you can see how the contours of an earthquake are reduced in a region from when earthquake occurred to the south and when another earthquake occurred to the north were reduced in this region in coincidence with the reduction of these ISO curves of vertical gravity gradient. So, and also analyzing the historic ruptures, also in this margin, we can see that this segmentation occurs. You can see that for historical earthquakes in the southern region of Sumatra, known as Mentawai region, because this archipelago is known as Mentawai Islands, you can see that the different historical earthquakes also occur between these lobes of vertical gravity gradient. There are some earthquakes that only occupy one lobe, and there are other earthquakes that occupy 2 or more lobes of minimal vertical gravity gradient. And always these regions where the vertical gravity gradient presents a more positive signal, you can see that segmentation is stronger. This in this region, as observed for the southern Chilean margin, the interseismic coupling between plates also agree with this gravity gradient signal. You can see that the higher slip, the higher interseismic coupling is associated to these minima vertical gravity gradients. Okay, well, this was the first point about the seismic segmentation that is highly related to high oceanic features, and the gravity gradient signal from GOCE replicates this segmentation very well. Then, and as a second point, we explored the relationship between gravity and high coseismic slip, because it's not only important why segmentation occurs, but it's also important to know why slip is enhanced or increased in some regions. A very great question for researchers, and it has not a clear response up to now. But I'll tell you something about the Megathrust. The Megathrust is a region between 15 and 35 kilometers in depth, and most Megathrust earthquakes occurs in this region. In these regions, this region has been characterized by Ley and Kanamori as there exist 4 domains in these regions. There is a region A, which is more close to the trench, where most tsunamigenic earthquakes occur. In this region, an elastic deformation and stable sliding occurs, but we have not a good resolution at this region because the forebulge presents a high gravity signal. You can see in these figures that the region described as region A, close to the trench, present a high gravity signal, and we performed some residuals, but you can't eliminate this high positive of the forebulge. This region A isn't also so wide, but the region B, which is the central part of the Megathrust, which is located mainly between the trench and the coastline, this region B is where most of Megathrust earthquakes occur. And in this region, asperities, that are those heterogeneities through the Megathrust that when an earthquake occurs, concentrate higher coseismic slip, they have high moment, seismic moment relief, and some of them also persist along different seismic cycle. These asperities in this region B are or present more area, and we can model with our data. The region C, which is almost behind the coastline and close to the cities, the region C presents more moderate landslides. Also, they are important. And in this region occur some minor patches, okay? And the region D, the final region, is a transitional domain where occur slow slip events and low frequency earthquakes. Well, but we will concentrate on region B and region C, where we have a better resolution and asperities are greater, so we can obtain better results. For the Maule earthquake, for example, this earthquake nucleated very close to the coast and propagated bilaterally to the north and south and presented different slip patches. We found that by modeling vertical gravity gradient up to 200 of the degree by cutting the degree and order of the harmonic expansion, at this degree order, we obtained an auscultation depth of the bodies of 31 kilometers approximately. This is the region where is located this megathrust. You can see that for this case, maximum slip, excuse me a moment, maximum slip occurred over vertical minima vertical gravity gradient lobes and presents a perfect adjust, and also that slip is reduced up to 0 at those regions where vertical gravity gradient present relative maxima along the strike. Another thing that we observed is that in those regions, perhaps the image is not so clear here, but in regions where the slip enhanced for this earthquake over the continental forarc, but to the east of the coastline and affected many cities, present also minimum vertical gravity gradients, as you can see in the first model, that represent some features or geological or body features that are more shallow. For example, if we compare the model up to 215, you can obtain an auscultation depth of 25 kilometers. And if you compare with the work of Higgs that performed seismic models, they found that gravity positives for the gravity anomaly coincide with seismic VP anomalies. So at the same auscultation depth, we obtained very close and very similar results that are indicating that the density structure along the margin is highly related to these seismic velocities. So this is another good news. Okay. For example, for the Arequipa earthquake, by cutting the degree order, and in this way we go in depth, okay, auscultating different structures, we can find also that for this degree and order, we can observe in a certain way the effect of directivity that occurred for this earthquake. This is another earthquake that nucleated at the point, but all the seismic energy propagated unilaterally and propagated towards this minimal gravity gradient lobe. You can see that here is a relative maxima in the gravity gradient. And when we go in depth, we can see a kind of channel to the energy, and the seismic energy propagates and enhances over the minima vertical gravity gradient. This was observed also for Illapel, for museum Ecuador, where also historical ruptures agree with the gravity gradient signal, and we can identify asperities in the region B and barriers to seismic propagation. For Sumatra Andaman, his is a better profile, where you can see how the slip is enhanced over minima gravity gradients. You can see that it's enhanced over minima gravity gradient, and slip in red is reduced where a maximum vertical gravity gradient occurs. Okay. The Sanda subduction region and to the south of the Sumatra earthquake and the Mentawai region present a very similar behavior. Historic earthquakes also agree. Here is a point, a very controversial point, because it has been analyzed why earthquake ruptured up to this point between these islands. And many authors said that in this region is a non-stable barrier. They said that in this region occurs a mobile barrier that sometimes acts as a barrier and sometimes it doesn't act as a barrier. And in this region, we have a signal lobe of minima vertical gravity gradient, and we can't find this or improve the discussion about this question. But to the south, you can see again two earthquakes nucleated very close to this relative maxima, and one earthquake propagates its seismic rupture to the north, and the other propagates to the south. And slip is again enhanced at minima gradient lobes. There is a very important question about the Sumatra region along the Mentawai archipelago, and is that maximum slip in this region didn't occur over the basins as occurred for the Chilean margin. In this region, the basins are between the islands and the continental line, okay? The basins are in this region, but slip didn't occur in this region. Slip occurred over the islands, and in the islands, we obtained these vertical gravity gradient minima lobes. So we were thinking that in agree with Wells and Song and Simons, that they said that maximum slip occurred over the basins, and this is not so true. This is not extensive for our margins, and perhaps we have to not to think about basins now and enhanced slip in basins, but in slip enhanced over these minima vertical gravity gradients, and find to which structures corresponds these vertical gravity gradients. Perhaps the accretional prism. There are many things to study and to explain why a minimum vertical gravity gradient in this region didn't occur over the basins, but over the islands. This is very important to be solved. Well, summarizing, there is a high inverse correlation between TZZ, or vertical gravity gradient minima lobes, and recent slip models. We can see this is the Tohoku earthquake, that highest slip occurs over these minima vertical gravity gradient lobes. Perhaps not always coincide perfectly as the Maule, because different plates have different particularities, dipping. So sometimes the models don't agree perfectly, but it's a very good approximation. You can see how slip is reduced, again, at the barriers, okay? And we can also observe for the Tohoku earthquake, the directivity effect. You can see that it's nucleated here, the earthquake, and maximum slip occurred to the minima gravity gradient law. And this not also agree with recent slip models, that is a quantitative relationship, but also is in good agreement with historical earthquakes or historical ruptures, which are modulated in a gross way, but qualitatively agree in a high way, and along different subduction settings. We can see that this occurs along all the southern Chilean margin, along Sumatra, along Mentawai, along Tohoku, and we are now exploring Alaska, which are the regions where most of or more giant earthquakes occurred. Then we calculated a spectral cross coherence between vertical gravity gradient and coseismic slips for these regions, and you can observe that this spectral analysis shows that there is a high coherence between slip models and vertical gravity gradient at the wavelength of the model at which we are working. Okay, this is very important because it's very quantitative. However, there is always an outlier, and the outlier is the Pisagua and Iquique earthquake that occurred a few years ago. This earthquake, when you analyze the signal, as you begin to go in depth or truncate the harmonic spherical development, you can see that the region where occurred maximum slip is over a positive. Okay, this is the first case, or the only case of all of cases that we analyzed, that is quite different. But in this region occurs something very interesting and quite different for the other margins, or the other sections of the margins analyzed, and is that the Iquique ridge is subducting just in this region. So you can see the effect, the positive effect of this ridge that is subduction under subduction in this region, and most of aftershocks occurred in this region, okay, of positive vertical gravity gradient. For this region, or this portion of the margin between Atacama and southern Peru, has been characterized as, mainly characterized as an erosive margin. The other margins are accretive margins, okay, but in this margin, the sediments along the trench are almost no sediments. It's starved the trench. Rains occur to the east side of the Cordillera de los Andes, and you have a desert along these latitudes. So the margin hasn't the supply of sediments, and erosion is occurring continuously in this margin. And here, the gravity gradient signal, the vertical gravity gradient, is related to the degree of intensismic coupling, but in a negative way. So we have to explore later this region, because it's very different, and well, you can see that didn't agree with the other region that we have studied. Finally, however, we performed geoid changes for the Pisagua outlier, and we found that if we compare different models by making the different successive models, GOCE models are not for doing this, but if you do, you can find that vertical gravity gradient diminished exactly in this region where maxima slip occurred. You have here the coseismic slip model, and the other models are after slip models. This region seems to have been locked, okay, where maxima slip occurred, and perhaps under some subsidence due to this locking, and to the north and to the south, perhaps the subduction was more occurring more free way, okay, and the vertical gravity gradient perhaps always also serves as a premonitor to modulate these changes along the margin. But unfortunately, GOCE has fallen down. We have no data to perform this. GRACE satellite has not a good resolution to perform this analysis, and we think that we need more gravity gradient satellite gravity gradient missions to focus on these changes. Well, concluding, for the last 3 mega earthquake, we can observe a great correlation between sleep models and the structure revealed by vertical gravity gradients with barriers and asperities, a very high correlation between these things. And we propose that our method allows mapping asperities, mainly in domains B and C. We can map barriers and attenuators, okay? We can infer directivity, assuming if an earthquake occurs in some region, we can say if an earthquake occurs here, it's probably that most seismic rupture propagate in that direction, okay? It's very important. And you can see that some asperities of the domain C can be mapped. These seismic asperities of domain C are very important to map because they are over the Earth area, not under the sea, okay? And most cities are in these coastal areas. So if you can map these asperities, perhaps you can help in the elaboration of seismic risk maps, okay? Well, concluding remarks are that these models have achieved an homogeneous accuracy, but still have a low spatial resolution, and we can only study these great earthquakes with very great rupture areas by truncating or cutting the degree order of the spherical harmonics development. We can map this region of the megathrust and achieve very good results when compared to seismic slip models. And we can map barriers, asperities. We have a quantitative relationship between vertical gravity gradient and slip. A good relationship with seismic structure as a function of seismic BP. A good relationship with interseismic degree of interseismic coupling, exactly for the region of Pisagua and Atacama, and a very good relationship with historical ruptures. And well, the best slip models that agree with our work are those who integrate geodetic data. Geodetic data or data are part of geodetic data, so it's not so suppressive that agree in a good way. Seismic data has information of higher frequency information. So perhaps with seismic data, you can map minor asperities, okay? And up to now with our data, we can't. And well, we think that it could be very important to find or to launch new satellites with this objective. And well, there are many more relationships and variables to analyze, and perhaps more questions than answers. Here is a little recordatory of different publications that we have performed in this subject. And okay, thank you very much for your attention, and excuse me if I was too large the presentation. I'm very bad my English.
Thank you, Orlando, for your presentation. It was the perfect time, 1 hour, so everything's fine. Well, before we begin our question and answer session, I would like to retribute the kindness. You said that you were well received here in São Paulo, and I too was very well received in San Juan. I went there 2 times in 2014 for a congress and 2015, where we collected magnetotelluric data together and also escaped from bulls in the Pampean plains. So it was really fun.
Yes, I remember that. Okay.
So,
Orlando is a gentleman. And
Hi, Carlos.
Mario. Hello, Orlando. How are you?
Very well, you?
Good, good.
So,
Nice to meet you.
So if anyone has a question, you may write in the YouTube channel and I read them to Orlando, or those who are here in the meet can ask directly to him. So I'll start. During your presentation, I was just thinking about if you could observe some change before and after the earthquakes, and then you show that you did that with the GOCE data. I didn't thought it was possible, really.
Okay. Really, GOCE models are static models. Yeah. So these models are like as EGM or Eigen. These models aren't for compare and to study temporal variations. These models are, and the data from GOCE is to perform this kind of atemporal gravity field. GRACE is was developed for this point to map differences in the gravity field. GRACE has been used for the study of glaciers, for hydrology, okay, but the resolution of GRACE is not enough, I think, for studying this. There are some works from GRACE for Tohoku earthquake, for Maule earthquake, then they take into account these changes in the masses inside the Earth. There are very, very good works about this, but not at the degree of resolution that we need or that we want. Yes. For example, this example of the Pisagua earthquake, perhaps methodologically is not correct because I performed the difference between two consecutive GOCE models that are static models, but one model have 1 year of difference with the other, for example, 1 more year of data, okay? Perhaps this data really is reflecting these changes. So we have to center perhaps in studying raw data, the raw data of GOCE. But I don't do that, okay? But I think that GOCE can show this because gradients were very precise data. And if you can compare this difference that I have shown with after sleep models, and you can see that after sleep was occurring to the north, to the south, and to the east, just in agreement with the gravity signal. This gravity signal perhaps is showing this, okay? But unfortunately, GOCE fall down, and Europe is not going to launch that I know a new mission. I know that Chinese are going to launch a new satellite. Now it's GRACE follow-on, GRACE FO, but I don't know what resolution they are achieving with this. The fact is that GOCE has or had better instruments than GRACE, and it was at the half height of Grace. Grace was at 515 kilometers. Excuse me, 500 kilometers, and Grace was at 215 kilometers. So GOCE was always falling down, and GOCE had a ionic engine, and always it was corrected for not to fall down. When the energy was used, bye-bye GOCE. So it's very difficult to measure with high resolution the gravity field with an spacecraft, because you have to always be pushing against gravity, and a lot of energy is needed for this. So it's very difficult to get a lower orbit, perhaps, to achieve a better resolution, because gravity field is inverse to the distance. So if you want a satellite closer to achieve better resolution, it's very difficult, technically difficult. But it's a problem, because you can measure gravity on the field, but over the sea, this is another thing. It's not the same to have continuous data. These regions are too wide to measure in another way than with a satellite. And the quality of satellite, I'm sure that is better than measuring with an aircraft, for example. Very, very good data, but, well, not for this.
Yes. Okay, thank you, Orlando, for the explanation on the satellites. Yes, I think that maybe if you have other examples of earthquakes that occurred during the GOCE mission, you could try to do the same thing with other earthquakes, but I don't know if there were.
Yes, we are working now with the earthquake that occurred last year in Alaska. There is a very good result, but I can't show now this. We are now exploring if these barriers are related to some faults, and we are analyzing this with focal mechanisms along the margin. We have an hypothesis, but this is very crude now, so I don't want to show, because
so in this case, the earthquake occurred last year, you said?
Yes.
So
year,
it is after the GOCE mission, so you can compare how things worked before and after. I don't know.
Yes. For example, for the Tohoku earthquake, there is a very good work from Fuchs. They showed that from GOCE that occurred before the earthquake, occurred many mass changes in the region of Japan, but the signal is too low. GOCE also was affected by Tohoku earthquake, because the particulates moved in the air, and the instruments that measure the orbit of the satellite measure these changes. And they said GOCE is the first seismometer on space, but really affected the satellite, and measured the effect of the earthquake on the air. It's very good. I think that perhaps not now, but in the future, with these works that are pointing to that, perhaps in a few years, the scientific community and the space agencies will take a better impact in this question about measuring earthquakes with satellites. It's not usual, because the community is accustomed to measure earthquakes with seismometers. Recently, with GPS, with INSAR, but now with gravity. It's
Okay,
a little
Orlando,
crazy,
yes.
but I think that it works.
Yeah. Well, thank you, Orlando. Let's see if anyone has any question to you. Well, on YouTube, we have no questions, so I don't know if anyone here in the Google Meet wants to ask something.
I just want to say thank you for your presentation. It's a very good one. I really enjoy it. So thank you for accepting the invitation for the presentation.
Muchas gracias, Carlos, por asistir también. Sí,
Gracias.
le preguntaba, I was asking for, Gabriel for you. I asked
okay.
Carlos Moreno still is working with you at USP.
Yes.
And Victor also?
Oh, Victor is
Susek?
now in Germany for a postdoc, but he was hired here. I think next month he will be back.
Okay. Very good. Very good.
Well, thank you, everyone, for watching. And the next presentation, I think, will be in the last week of July, so we don't have presentations on the next 2 weeks. Thank you, everyone, and see you.
Thank you for you. Thank you very much.